All right, we've got this charge of 18 microcoulombs just sitting here, negative 18. It's just sitting there. Over here, we've got a charge of plus 4. And for some reason, we push this plus 4 closer to the 18. So it starts off that it was way over here, 25 centimeters away. And it ends up that it's here, only 10 centimeters away. How much work would it take to get it from that 25 centimeter position to the 10 centimeter position? Before we do the math on it, what do you think? What's your guess? Is the work going to be positive or is the work going to be negative? We'll do it mathematically and hopefully our math matches what you think logically. To do a question like this, work, whether it's electricity or gravity or any sort of field situation, work is always the change in energy. So in this case, it's going to be the change in electric field energy. Change in is always the second value, take away the first value. So it's electric energy in the second situation, take away electric energy in the first situation. Now, in a way, it turns into a plug and chug. Electric energy is always KQQ over R. So this one's going to be KQQ over R2. Take away KQQ over R1. Now, I'm not going to solve it this way, but I just want to do one little common factor. If I pull out the little q, then I'm left with KQ over R2 minus KQ over R1. KQ over R is voltage. So really this version here, what I'm saying is that the work to do something is Q times the change in voltage. Electric potential is often looked at in terms of differences, and this is kind of why. Work is the little q that we happen to be moving around multiplied by the electric potential difference, or the change in volts. We could solve the question from here. I just wanted to show you the change in volts, but it'd probably be smarter to do a little bit more factoring. To find the work, it's KQQ, factor all three of them out, and then 1 over R2 minus 1 over R1. Plugging in our values, K is 9 times 10 to the 9. Q this time was negative 18 microcoulombs. That's 10 to the negative 6. Because work and energy are scalars, it's important that I put the negative with it. The charge that we're moving, little q, was 4 microcoulombs. And then we got to switch to meters, but our second distance was 10 centimeters, so this is going to be 1 over 0.1. Our first distance was 25 centimeters, so 1 over 0.25. It's a little bit ugly, but if you do a little bit of math in your head, 1 over 0.1 is actually 10, and 1 over 0.25 is actually 4, or just plug and chug it into your calculator. When you crunch it out, we end up with a negative number. Hopefully you suspected that, and the value is 3.9 roughly in joules. If you go back to the kind of setup of this question, we're moving a positive closer to a negative. It wanted to go that way anyway. So when we move it from the 25 position to the 4 position, or the 10 centimeter position, it would have fallen that way on its own. So if anything, we need to push the 4 away from the 18 to stop it when it gets to that 10 position. So the way I've drawn it, the 4 is being moved to the left, but in a way to control it, we had to push it to the right. Opposite direction leads to a negative in our work situation. Or just think the fact that we're moving it to where it doesn't want to be, we're moving it to a lower energy position. That means it doesn't take positive work to make that happen. Different ways to think about it. Hopefully you can connect or resonate with one of them.